Okay, so we're back here continuing to talk about pipe flow, and in the last video we looked at pressure losses in pipes and we introduced the idea of the Darcy-Weisbach equation, and this is commonly used to estimate head loss. And so head loss is a way of thinking of energy losses in terms of units of length. And it seems maybe a little weird, but you'll get used to it. This is the way we typically do it, especially in hydraulics. And so part of the Darcy-Weisbach equation for estimating head loss is knowing the friction factor. And so we said that there would be very different analysis used for laminar and turbulent flow to get those friction factors. And so in this video here, we're going to look at the friction factor for laminar flow. We're going to start that analysis. So because of energy losses, we can't really use Bernoulli's equation to figure that out. So we need something else. And so momentum has to be conserved, and that means that we can use the Navier-Stokes equations, which are a conservation of momentum, to analyze the velocity at different points in a flow field. And so remember, this is the Navier-Stokes equations we've written before, and this is in 3 dimensions. So this del operator can have an x, y, z component. And remember, we have pressure here as an unknown, and then we have velocity in 3 dimensions. So this is like 3 different equations with 4 unknowns. But we can actually analyze this one. Most of the time you can't solve it, but we can analyze it for laminar flow and come up with an equation. So we're going to go through how you get that equation, where it comes from in this video, at least the starting point for that. And so remember, this first term represents convection, and we looked at in our dimensional analysis chapter the Reynolds number, which we said represents inertial forces versus viscous forces. And so our viscous forces here are represented by this term, and then our inertial forces here from convection are this term. And so because we're looking at laminar flow, basically the convection term is not important because it's laminar. So we can make that assumption. And we're going to be looking at a horizontal pipe here for starters, and really this applies to non-horizontal conditions too, but gravity is also not going to be very important because it's horizontal for this analysis. Okay, so really we've already gotten some progress. Remember that V is really in 3 dimensions, and so if we're analyzing a pipe, we could use x, y, and z coordinates, but it actually makes a lot more sense, and it makes this doable and simpler if we do it in cylindrical coordinates. So a cylindrical coordinate system is one where you have a z-axis that you go up and down along the cylinder, and then you can go out from the center along the circle, and then you have some angle you use to describe the position. So some point is going to have a height above the circle, some distance from the center line, and then some angle from 0. And these are the 3 we use instead of x, y, z in cylindrical coordinates. And so that's what we're going to use here. And if we think about laminar flow, remember we have like a Q going this way. We are trying to predict the velocity here at different points inside this pipe. So if we go down the pipe, we're going to assume assume it's long and steady. A lot of assumptions. And so really what that means is that the velocity profile is going to look the same everywhere. So if I go in the z direction, so dv by dz is going to be 0. Nothing is changing if I go this way. Thinking about laminar flow, remember, in laminar flow, if I follow a streamline, like say this point, it's not going to move up or down as I go along the length of the pipe. What that means is it's not going outward. If we were to look at it from this side, it's not going to move outward further, and it's not going to spin around. So really that means that VR and V theta, velocity moving around the circle here, okay, those are both 0. We can ignore those. So that means that V has just become V in the z direction. That's the only one left. That is the velocity this way, and it's really not changing as we go down the length of the pipe. So all these assumptions are going to allow us this to become a little simpler. So we got rid of those 2 terms, which means that we're just left with del P, if I move it over is equal to mu del squared v, and then we said that v is equal to del squared, that v is just going to be vz because the other two components are going to be 0. So now I'm down to one dependent variable that I'm trying to find, and so then that makes things a little bit simpler. So now we need to know what to do with these gradient terms. So in rectangular Cartesian coordinates, we have, remember that d by dx I plus d by dy j plus d by dz k. This is our gradient vector. Okay, that's our del. Or if we do del squared, which is really the dot product of this with itself, that means we do this one times itself, and it becomes a scalar. That gives us d squared by dx squared plus d squared by dy squared plus d squared by dz squared. So the ijk terms go away. So this is what it looks like in rectangular coordinates, but we're actually working in cylindrical coordinates, so these look different. And so we're not going to talk about where that comes from, but we can just kind of say that basically these are the versions of del if you're in this other coordinate system, and it looks a little bit different. But it can be convenient, again, to do it this way because we can actually solve the equation if we use cylindrical coordinates. So del f of some function f here, if we have unit vectors in the r, theta, and z direction, these are the partial derivatives in each of those. So f and z look similar to x, y, z, but this theta term, because it doesn't have because you're just going around, it has to have this 1 over r in there to make the units work out. And then likewise, our del squared, when you do this with itself, the dot product in these coordinates, this is what del squared ends up looking like. So you got a 1 over r d by dr of r df dr. So this is kind of looks messy. But again, we can simplify things, and we've got these other two terms here. So anyway, but given these definitions for del f and del squared f, now we need del p. So basically just taking the f and making a p out of it. And the pressure, basically, we're going to assume that the gravity effects are negligible here. We've kind of already said that. So if you spin around this circle, or if you go out to different points in the pipe, the effects of gravity are not going to be changing appreciably. So really, okay, gravity not changing. So it means we can get rid of those two. And so then F becomes P, and so we're just left with del P is D dP by dz. Okay. And we already talked about in the last video how the pressure loss is going to be a constant if you're looking at a steady flow, and so it's going to be a constant value of delta P over L, and it's going to have a negative value because the pressure is going to be decreasing. So this takes this gradient vector basically and just turns it into a constant number. Much easier to work with. Okay, and remember we need this one because our equation that we simplified to is here. So we need to get rid of this, and now we need to deal with this one. And so del squared V then is going to be, we're still going to have this term, so it's messy looking, but we're breaking things down. dvz by dr. And then because of its laminar flow, we said that the velocity, if I look at the velocity here going like towards us, if we're looking at this pipe from the side, the flow is coming towards us. We don't really have any reason to think that the velocity is going to change at different at different angles as I move around the pipe. It's going to be symmetric, so it's going to have some symmetric value here. We're going to expect it to get bigger in the middle and then go to 0 at the sides because of that no slip boundary condition. So there's not any velocity moving out, and we don't really expect it to change when we go this way. So that allows us to basically say by symmetry, yeah, so this term by symmetry goes away. And then we said that it's not changing as we go down the length of the pipe. So if I go in this direction, the velocity is the same at the middle all the way down the length of the pipe, and all the way down the length of the pipe it's going to be 0 along the wall. So it's not changing that way. So constant along, constant v, z along pipe. So many assumptions, but these things all drop out, and so now, boom, we have taken that crazy partial differential equation, and we have the pieces that we need here. And so remember, the equation that we had gotten to on the last page was delta p equals mu del squared vz, and now we're saying that we can replace this with this negative delta p over L constant, and then we still have our mu, and now our del squared v has become 1 over r d by dr of r dvz by dr. Okay, so now we're down to something that we can actually work with. So remember here, this still looks messy, and I know that it probably looks difficult for you guys. You're not used to seeing it, but it's much easier if we can keep in mind what kinds of variables we're working with here. So remember that vz here is the thing that we are trying to predict. We want to be able to know what the velocity is at different points inside this pipe that has laminar flow. So we think it's going to be the same going down the pipe. We're ignoring entrance effects and assuming it's steady, but it's going to change if I go from the middle to the outside. Okay, so we expect it to be like 0 at the wall, no slip condition, and then bigger in the middle. So we're trying to predict v as we go out in the r direction. So v is our dependent variable. So it is not a constant, okay? And then the thing that it depends on is r, so it's our independent variable. And then we have also delta p, L, and mu. So delta p, L, mu. These are constants. These are not changing anywhere. These are our parameters. Okay, and so again, it's really helpful to understand this designation, both from the point of view of understanding the system and then also to do the math now. So what does that mean? Basically, what I can do here now, I can solve this by integrating. So I'm trying to come up with an equation for v versus r. The v and r are not constants, but delta p, L, and mu are. So I'm going to move all those together, and I'm going to move this r over here. So I get a negative delta p over mu L times an r. So I moved these guys over here, and now that's got to be equal to, and I'm also going to move over, the dr. So I'm going to move mu r and then the dr in the bottom here, and that's going to leave me with, I'm just going to write that as dr. So the partial derivatives are really just regular derivatives now, and that's going to leave dr by dvz dr. Okay, so the d here gets left behind with this, and then all these other guys went over there. Make sense? Okay, so we can integrate both sides now, and remember these things are constants, so they don't do anything, but the r isn't a constant. So when I integrate it, I've got a negative delta p over mu L, and then r becomes r squared, and then I need a 2 there to cancel that out if I do the derivative. And now I'm going to have an integration constant. Okay, so there could be a constant of integration, and this thing, the integral of the derivative, just is left with what was there before. Okay, step 1. And now the next step is, okay, I need to get vz by itself, so I'm going to move the r and the dr over again and integrate again. So I move this r over, and I've got negative delta p over 2 mu L, and now there's just an r left once I divide it, and then plus c1 over r, and then that whole thing is times dr equals dvz. That's what's left, and I can integrate again. And so now I'm left with negative delta p, and so when I do r, this becomes r squared again, and then I need another 2 there, so 4 mu L times r squared, and then integral of c is a constant, but 1 over r has a derivative of natural log, okay, natural log of r. And now I need a second integration constant, and that is Vz. So I've gone through this huge exercise, and I have actually come up now with an equation for velocity at different points in the flow field R. Not changing as I go in the z direction, not changing as I go around different parts of the circle, but going from the middle to the outside, I have an equation that I can use now. But I'm not quite done because I have these two constants that I need to find. How do we find the constants? We need some other information. What is that? Those are going to be our boundary conditions. The boundary conditions are needed to find the integration constants. And so remember, at the outside boundary, we know that Vz has got to be equal to, at R is equal to what I'm going to call big R is equal to 0 from the no slip condition. Okay, so big R here is the radius of the pipe. Little r is the distance. Okay, so little r is a variable, big R is a constant, it's a parameter. Makes sense? And so on the outside, the velocity is 0. This is our no slip condition. So that's going to be 1, and we need a second one though because we've got two constants. Second order equation here when we started. And so the other one is going to be basically this idea of symmetry. And so we expect that at the middle of the pipe that it should be symmetric if you go outward from there. If you look at the middle, nothing really should be changing. There's nothing forcing at one side or another, so this whole thing should look symmetric. And what that means is that the derivative at the middle needs to be equal to 0 for that to be the case. So dvz by dr at r is equal to 0 has to be 0 because of symmetry condition. Okay, so now I need to plug these things in and get C1 and C2, and then I'll have my equation for the velocity at different points. So I'm actually going to use this one first because it makes things easier. So to use this one, I've got to take the derivative of this guy. So dvz by dr up here is going to be a negative delta p over 4 mu L times a 2r. So this is a constant, and this is what I'm taking the derivative of. And then plus C1 over R, and then the C2 goes away, and we're saying that that has to equal to 0. That's what this equation says. And so what value of C1 here is going to make this right, and so this is at R equals 0. Now I have to remember, okay, so if I plug in R equals 0 here, because we have R equals 0, that goes away. So basically this just tells us then that C1 has to be 0. Okay, and so now we're down to Vz as a function of R. That's this whole equation. We've now determined, because of our symmetry condition, that C1 has to be 0. And we're left with C2 minus delta P over 4 mu L times R squared. Okay, and so we need C2, and so to get this one, so again, I'm just rewriting this one and making that substitution. Now we can use our no slip condition. So R is equal to big R. We have Vz at R is equal to big R is equal to 0. And if I plug the big R in here, I've got C2 minus delta P over 4 mu L times big R squared. So therefore, C2 has got to be delta P over 4 mu L times big R squared. And so again, remember that big R is a constant. It's a parameter. It's a constant because it's the radius of the pipe that we're looking at. So if I go back and plug that in here, you'll see I have this delta P over 4 mu L term, and it's at both of these, and so I can factor that out, and that leaves behind a big R squared minus little r squared. So Vz of R is equal to delta P over 4 mu L times big R squared minus little r squared. And if I wanted to write this with diameter instead of radius, because we often work with the diameter, then I would have delta P over 4 mu L times d squared over 4 minus r squared. So either one of those is right. So this is now an equation we've gotten for the velocity at different points given these parameters about the field, some pressure drop per unit length, the viscosity of the fluid, and then the diameter of the pipe, assuming we're in a laminar flow situation, long tube, etc. But all these things are actually reasonable assumptions, and so this gives us the velocity. So this is something that we've talked about in the previous chapters, and what we want, remember, is to come up with a way to predict the energy losses so that we can do engineering designs, okay? But we have to have all this theory to come up with an equation we can use. And once we have the velocity, we can now go and come up with a formula for the friction factor, and we'll do that in the next video.